So today we are going to look at different types of chemical reactions. The first one that we're going to look at is called a combination reaction. Sometimes it's also referred to as a synthesis. Synthesis really just means to build. So this is a reaction in which two or more substances combine to form a single new substance. It will have this general format: A plus B yields AB. So when we write things like this, if they are written side by side, this indicates a compound, whereas a lone letter will indicate an element. There are different types of combination reactions. We can have two nonmetals combining to form a molecular compound. We can have combination reactions that use transition metals. If you might notice that, remember, transition metals could have different charges, so you'll have to be careful about that when you're going from like the words to the symbols and making sure you have the appropriate charge for with what the transition metal is combining with. And then the third type is a metal and a nonmetal, which will form an ionic compound, like forming sodium chloride. You need to remember this. This is huge, especially after needing to go through number 9, and it was a lot of diatomic molecules on that. You need to remember to watch out for your diatomic elements. So as a refresher, your diatomic elements include hydrogen, nitrogen, oxygen, fluorine, chlorine, whoops, not a plus sign, bromine, and iodine. So if you have any of those in an equation and they are not combined with another compound, you need to indicate that they are a diatomic element. If, per se, you have like sodium in the equation, since it is not a diatomic element, you can just write it as Na. It doesn't need the subscript 2. So potassium is a very reactive alkali metal because it is found in that first family. And it actually has to be stored under oil because it will react with air. So I would like you to practice writing the chemical equation for the combination of potassium and oxygen. So why don't you sketch out a skeleton equation? All right, so what did we get for a skeleton equation? Cora?
K plus O2 yields KO2 without like solid
KO2. How do we feel about that? Potassium's good. It's not a diatomic. She caught that oxygen was the diatomic. What about our compound? Ionic or molecular? Ionic. Are the charges balanced out to 0 in this as it's written? It is not. So we need to make sure we balance out the charges. Potassium has a +1. Oxygen has a -2 charge. So we do not need this subscript at all on the oxygen. Rather, we need it here on the potassium. Okay, so we have that for our skeleton equation. And then we need to balance it. If you are asked to write an equation, even if it doesn't say to balance it, your final answer must be balanced. Okay? So how are we going to balance this equation? Didn't we just do it on the other number 9 something? Cora? Okay. Are our oxygens okay? Nope. Oxygens need to be worked on. How do we fix our oxygens? Kenzie?
Put a 2 in front
All right. Does that keep our potassiums okay? Nope. We need to change this 2 to a 4. Are there any questions? This section is going to be almost identical to yesterday, except that you're going to have words that indicate the type of reaction that it is. So our next type of reaction that we're going to look at are still combination reactions. It's telling you that elements can react with a compound to form a new compound. The point being with combination reactions is that you only will have one product. So we can combine 2 compounds to create a more complex compound as long as we still only have one product. You could have 3 reactants and it still be a combination reaction as long as you still only have one product. Now, our second type of reaction is a decomposition. This is a reaction in which a compound breaks down into 2 or more simpler substances. Your general form is AB yielding an A plus a B. In order for a decomposition reaction to happen, there has to be some kind of energy source inputted into the reaction. So I think yesterday in that table it showed you like with an arrow with a delta over it indicating heat being added. Sometimes electricity, so they'll abbreviate electricity over the top of the arrow. Those are ways to indicate that something else other than a compound or an element is involved with the reaction. So the simplest kind of a decomposition is the decomposition of a binary compound. A binary compound will only have 2 elements in it. Bi meaning 2. 1 or more products may still be produced. So when we look at mercury oxide here, it breaks it down into the mercury and the oxygen. Metal carbonates decompose to give us metal oxides and carbon dioxide gases. Metal hydroxides decompose to yield metal oxides and water. And some unstable acids decompose to produce non-metal oxides and water. Do you really need to know those? No, because you'll figure it out in the reaction. I'm not going to ask you if this is a metal carbonate decomposing. I really would just prefer you to understand that it's a decomposition reaction. It's not going to get into that kind of details. So for this example, when an electric current is passed through pure water, it decomposes into its elements. Write the balanced equation for the decomposition of water. So why don't you give this one a whirl on your own here. All right, what did we get here? You can just give me the skeleton one. Cora.
You have to have where you have the parentheses and then A2 or something after it.
If you want to, but it would just be liquid because it's water.
Yeah, I know.
Oh.
H2 and then in parentheses L.
Okay.
And then electricity with the arrow.
Good.
H2G plus O2G.
H2G plus O2G. Good. So for a skeleton equation, this encompasses everything that we were given. Your water, that's balanced there. Your hydrogen is a diatomic, that's accounted for. And the oxygen is also a diatomic, and that is also accounted for. Now the last step is just to balance it. So looking at the hydrogens, those look balanced. Moving on to the oxygens, you have 2 on the product side, 1 on the reactant side, so we will need to put a coefficient out front. Yep. Yep, we'll put a 2 out here. That balances off our oxygens, but then it throws our hydrogens off, so we need to balance on the product side. So we'll put a 2 out here, the 2 times 2 here for 4, and the 2 times 2 here gives us 4 as well. Are there any questions on these?
Do we need the liquid gas phase?
Do you need them? No. Is it a good habit? Yes. Because we will get to a point where we need to indicate when a solid is produced, but that's not for a couple chapters. So you just need to be prepared for that to sneak back into your life and then become a requirement. Okay. Single replacement reactions. This is a reaction in which one element replaces a similar element in a compound. Your general form is A plus BC gives us B plus AC. If A is a metal, it has to replace the metal in the compound. If A is a nonmetal, it has to replace the nonmetal in the compound. You can't switch them up. This is very important here. Hence the red, underlined, bold, all capitals. A single replacement reaction will only occur if the element doing the replacing, that would be indicated by the A in the general form, is more reactive than the element getting replaced. So whatever element A is going to kick out of the compound has to be less reactive than A. Okay, so remember our reactivity trends from a couple chapters ago? That's sneaking back up into this. So, practicing this rule. Why does this reaction take place? So we're looking at magnesium and copper nitrate becoming magnesium nitrate and a lone element copper. So magnesium is replacing what element? Magnesium is replacing copper. So based on your knowledge of reactivity, is magnesium more or less reactive than copper? Is it farther to the left or the right? Left. It's farther to the left. It's more left, so it is more reactive. With metals, your most reactive elements are towards the left. So since magnesium is more reactive than copper, yes, this reaction will happen. So now when you are given a reaction, if you identify that it is a single replacement reaction, you will also need to investigate if it will actually occur. Okay? If the element in the compound is not reactive, it will not happen. Or sorry, if that A element, that first lone element, is less reactive than the element in the compound, the reaction will not take place. You do not need to write out the reaction. All you need to do is write NR for no reaction. If you can identify these problems, you will like them because there's not much work to them. A couple different types of single replacement reactions. Again, I'm not concerned that you can identify these hydrogen replacements or very reactive metal replacements. I just want you to identify if they are single replacement, and then furthermore, if they can actually take place. So, to help you identify if an element is more reactive than another, there is this handy dandy table. I will not guarantee that this will always be part of your tools, so you should get fairly comfortable with this on your own. On the left-hand column, this is your activity for metals. So if it's at the top, it is more reactive. And if it's at the bottom, it is less reactive. The right-hand side are your nonmetals. Again, the top is more reactive than the bottom. So there's two equations on the right-hand side, nickel and lead nitrate, and then nickel and iron nitrate. I want to know, based on the activity rules or that activity trends, which one will happen and which one will not. So to do that, you need to compare nickel's reactivity with lead for the first one, and then nickel, compare it to iron, because we have to compare the metals. Since nickel is a metal and it's replacing a metal, you have to look at the two metals. So you need to ask yourself, looking at nickel, find it right here, where does lead fall? Below it. So is nickel more reactive? Yes. So then this reaction will happen. So then nickel again, and this time we're looking at iron. Iron falls right here. Is nickel more reactive than iron? No, so the reaction will not happen. Does that make sense?
Yeah.
Okay. Leroy, are we good on that?
Yeah.
Okay. So then to practice this, use the activity series to predict if the following reactions will occur, or if not. If the reaction does occur, you need to write the products of the reaction and then balance the equation. So back to Daniela's question about if you need to write the parentheses with the state of matter. If you're given half an equation like this and they're provided to you, then your products would also need to have them. How about that as a rule? So what two elements for reaction number 1 do we need to compare? Aluminum and zinc. So going back to this chart, you find aluminum here, and then you find zinc. Is aluminum more reactive than zinc? Yes, so the reaction will happen. So we have ALS plus ZnNO3 2 aqueous, and we get zinc by itself, and then AlNO3 3. Why do I need this 3 here? Hint, look at the charge on aluminum. Aluminum's +3. Nitrate is -1. So this subscript 3 is to balance out the compound. Do I need to do anything to zinc? No. Other than we need to put if it's a solid, liquid, or a gas. Zinc is a metal. At room temperature, metals are what state of matter? Solid. And then aluminum nitrate. If the compound starts aqueous, the new compound will also be aqueous. Unless the new compound is just straight plain water, then it'll be a liquid. Liquid water cannot be an aqueous solution on its own because it's redundant, water with water. So next step to balance. It looks like the only thing that's off are the nitrates. On the reactant side we have 2, on the product side we have 3. 2 and 3 have what number in common? 6. So on the reactant side, to get 6 with this 2, we need to put a 3 out front. And on the product side, to get a 6 on the nitrate, we need to put a 2 out front. That messes with both zinc and aluminum. So to fix the aluminum, we throw a 2 out front, and the zinc will get a 3. Does that make sense? Okay. So then, looking at number 2, will number 2 take place or not? All right, we have 2 more types of reactions to happen or to go through. The first one is a double replacement reaction. This is a reaction in which the positive and negative ions of the two ionic compounds exchange places to form new compounds. This is your general form. AB plus CD gives you AD plus CB. This generally will occur between substances in aqueous solutions. You can produce a solid precipitate. That means that the solid is not soluble. That means it cannot dissolve in the liquid, and you will get a solid. We will discuss this more in a couple of chapters. You can get a gas that is produced, and you can also form a molecular compound. Your most likely one will be water. Again, I'm not too concerned about the states of matter here versus your ability to identify this is this is a double replacement reaction. So write and complete the balanced chemical reactions for the following double replacement reactions. I think for this particular one, we'll just look at, we can either do both of them and then not balance them because we're short on time, or we can just do number one and completely work the whole problem. Just number one the whole way through. Okay. So number one, you have to just switch up the partners. So in this particular one, sodium's the positive and the hydrogen is the positive. So instead, write the equation. HBr gives us your Cn, your negative one, will stay on that side. But instead of it pairing with sodium, it's going to pair with the other positive option, which is hydrogen. And then your bromine will pair with the other positive, which is the sodium. You see that, just switching the partners around? So then this one's given to you as aqueous. This one's aqueous. It says hydrogen cyanide gas is formed, so that'll be a gas, and this will stay aqueous then. And then we can balance. It is balanced, isn't it? Everything's one? Perfect. Are there any questions about how to go about the double replacements? Okay. The last type of reactions are called combustion reactions. This is a reaction in which a substance reacts with oxygen gas, releasing energy in the form of light and heat. This must involve O2 as one of the reactants. Most of the time, you'll just be given one reactant because it is assumed that you know the second reactant will be O2. Combustion happens with hydrocarbons. These are compounds made up of only carbon and hydrogen. And the products of combustion of a hydrocarbon will always be CO2 and H2O. So, last example, I believe, for the day. Combustion reactions suck to balance. They are by far the most putsy. You will do a lot of trial and error with them, okay? That's just the way they are. So ethanol can be used as a fuel source. The formula for ethanol is C2H5OH. Write the balanced equation for the combustion of ethanol. So that right here indicates what is the other reactant. The other reactant must involve O2 as one of the reactants. Do we have O2 as a reactant yet? Nope, so it has to be O2. And then what are the products of a combustion reaction? CO2 and H2O. CO2 plus H2O. So then here ensues the fun of balancing. The recommendation for this is always balance your carbons first, then your oxygens, and then lastly your hydrogens. That kind of helps alleviate some of the issues. So looking at our carbon, we have 2 to 1, so we need to put the 2 out front here. So then we follow the kind of guideline rule looking at oxygens. There's 1 here, plus the 2 here, for a total of 3 on the reactant side. Here we have 4 oxygens plus 1 for a total of 5. So how do we want to go about fixing this? What did you say, Daniela?
Add a 2 in front of the single diatomic.
Right here?
Yeah.
Add a 2 there. Okay, so now that puts us up to, this is 4, and that makes 5, right? Okay, so that's good. So then let's look at the hydrogens. There's 5 and 1 is 6 over here. And how many do we have here just? 2. So how do we go about fixing that? How many do we need on the product side? We need to put a 3 right here. 3 times 2 makes 6. So now we're 6 and 6, so that's good. However, putting the 3 here messes with these oxygens. So now we have the 4 oxygens right here, plus the 3 over here, for a total of 7. See what I mean? They're kind of a pain in the butt. So if we change this 2 right here, this 2 to a 3, how does that fix things for us? So now we have 1 oxygen here, plus 6 oxygens from here, for a total of 7. Does that work out how we need it to? Yes. So that would be your final answer on that one.